Hello, I'm back with another set of oscillations questions. So I've got three in this video. We're starting here with a displacement against time graph for an oscillating mass. Wonderful. Use this graph for the oscillations of the mass to determine the amplitude, the period and the angular frequency. Right, well, the first two, amplitude and period, we're just reading these straight off. Amplitude is maximum displacement. So our A is 0.4 meters. Our period is the time for one oscillation, so that's going from there to there, which looks like 5 seconds. The angular frequency, omega, is 2 pi divided by the period. So we've got 2/5 of pi on this, which is about 1.26, so 1.3 radians per second to two significant figures. So that was straightforward. Mark with a cross using a different position in each case, the point where the velocity of the mass is a maximum, acceleration of the mass is 0, potential energy of the mass is a minimum. Right, okay, so this is interesting. So velocity being a maximum, you think what it's like when you're on a swing, you come to a stop when you're at the amplitudes, and you're going quickest when you're at the bottom, when you've got 0 displacement. So we want any one of these points where it's intersecting the x-axis, where we've got 0 displacement. So that's a v. It's going to be similar for the acceleration of the mass, because we're only going to get acceleration if we've got force, and we've only got force if we've got displacement. So yeah, this is the whole point of SHM, isn't it? That acceleration is proportional to the displacement and directed back towards the equilibrium point. But in terms of magnitude, it's going to be a minimum at no displacement. So that's our A. And then same for potential energy. If we've got a maximum kinetic energy, we must have a minimum potential energy, because we're just passing backwards and forwards between kinetic and potential. So that's going to be a P. So any 3 points that are intersecting the x-axis and you are fine. Right, last part, cone in a loudspeaker oscillates with SHM, vibrates with a frequency of 2.4 kilohertz, amplitude of 1.8 millimeters. Calculate the maximum acceleration of the cone. So A max is A omega squared. This we'll be familiar with from all of our analysis of SHM. It's in the formula booklet, but it's also something we've been through on one of the previous videos explaining all of that. What are we doing? We've got omega is, of course, 2 pi f. So we want 4 pi squared a f squared is going to be our A max. So that is 4 pi squared a squared. So that's 1.8. No, A, just A, not A squared, is f squared, isn't it? So 1.8 times 10 to the minus 3 multiplied by f squared. So 2.4 squared times 10 to the 6. Right, it's quite a lot to type in. 4 times pi squared times 1.8 times 2.4 squared, 409, and then multiplied by 10 to the 3 that we've got left. So that is 4.09 times 10 to the 5, which is 4.1 times 10 to the 5 meters per second squared, to two significant figures. Good. Cone experiences a mean damping force of 0.25 newtons. Calculate the average power needed to be supplied to the cone to keep it oscillating with a constant amplitude. Okay, so we want to let's look at this over one oscillation. Well, I mean, you don't necessarily need to even do that. We could do it over a quarter. So if we got the average damping force is 0.25, so the work done in a quarter of an oscillation, let's just stick with that, is going to be force times distance. So 0.25 times the 0. I'm looking at the graph. We're on the loudspeaker still, aren't we? So 1.8 times 10 to the minus 3. So that is the work done. That's in joules in 1 quarter. So we need to do energy over time. So therefore the power is going to be equal to whatever that is, divided by a quarter of the time period. So it's going to be that 0.25 times 1.8 times 10 to the minus 3 divided by t over 4. So we can get rid of that and then divide by 3 t. So t is, we've got the frequency, haven't we? So yeah, it's 1 over f. So we need to multiply by f instead of dividing by t, which is 2.4 times 10 to the 3. The 10 to the 3s are going to cancel, so it's going to be 1.8 times 2.4. So we need to double it, so that's 4.8, and then take off a fifth of all of that, which is minus 0.48, which is 4.32. So 4.3 watts to two significant figures. So yeah, we didn't even need a calculator for that, because again, they've given us some really easy numbers. The main thing with the power, I mean, it doesn't, I've picked a quarter oscillation here. You could pick a whole oscillation, you know, any part that you want. I mean, but you want to really pick it in multiples of quarters, because then you know how far that we've actually moved. It makes it a lot easier, because we're going up in blocks of these 0.4 meters. So if you've done a whole oscillation, then we've got 0.4. Oh, again, I'm looking at this blinking graph again. Sticking on this one with a 1.8 millimeters. So you've got that 1.8 millimeters for every quarter of the oscillation. That's how far you've moved. Or if we were going back to this one on the graph, as I seem to want to do, every quarter of the oscillation is going 0.4 meters. So we can just do, because they've given us a mean force, we can do a force times distance, and then you just divide by time to get the power, because power, of course, is the rate of work done. So we have to divide by time to get our wattage. So yeah, it's a nice question. Right, now we're starting. Oh, looks like we're going to get one of the tied questions. I always like these ones. We're starting with some definitions though. So for a body undergoing simple harmonic motion, describe the difference between displacement and amplitude. So displacement, that is the distance, well, and direction, I suppose, from and direction, because it's not just the distance. So you could say a vector distance, but distance and direction from equilibrium point. And the amplitude is the maximum displacement. Maximum displacement. Cool, so that's good. And then the difference between frequency and angular frequency. Okay, so that's an interesting one. So the frequency is the number of oscillations per unit time. Usually per second, but we can use any time unit. And then the angular frequency is it's 2 pi multiplied by the frequency. So this is then going to be in radians per unit time. Radians per unit time. So you don't really need to get into a discussion about trying to give a description of angular frequency in words. I mean, you've got, because otherwise you have to get into the description about the associated circular motion of simple harmonic motion, of an oscillation such as that. We've been through this in the other videos of how if you've got something which is oscillating in one dimension, then that is closely related to circular motion in 2 dimensions, in a plane. That this oscillation is the diameter of that circle. So by looking at angular frequency, rather than having this linear path of something that's moving at variable velocity along a straight line, we're talking about something that's moving at a constant speed in a circle. So we cover that in more detail in one of the other videos, but that's why angular frequency is so useful. But yeah, just say it's 2 pi times the frequency. Right, so a harbour represented in figure 4.1 has vertical sides and a flat bottom. The surface of the water in the harbour is calm. Okay, they've given us some depths here. The tide causes the surface of the water to perform simple harmonic motion with a period of 12.5 hours. And then they've given us these 2 depths that are on the picture. So for the oscillation of the water surface, calculate the amplitude. Right, well, if that's the high and low, then the equilibrium, our midpoint is, well, by definition, a midpoint is in the middle. So we need to get the amplitude is going to be half of the distance between high and low. So it's going to be 2.5 meters because we've got a 5 meter difference between maximum and minimum. So half of that is 2.5. The frequency, well, I mean, you can write this in different ways. As we've set up here, we've got frequency as a number of oscillations per unit time. So yeah, I mean, they've given us the period here. So frequency is 1 over the period. So we don't have to have it in seconds. We could say it is 1 over 12.5 and then say hours to the minus 1. That would be fine. So what's that? 2 over 25. So 0.08 hours to the minus 1. Or you can put that in and say, okay, well, let's actually turn those hours into seconds. So 12.5 times 3,600, and then do 1 over that, and you get 2.2 recurring times 10 to the minus 5. So we could say it's 2.2 times 10 to the minus 5 hertz, which is seconds to the minus 1. And yeah, we normally do hertz. I mean, that's why seconds to the minus 1 has been given its own title, because it's the one that we tend to use. Either of those are fine, though. It doesn't matter, providing you've specified what the time unit is, then it's okay. Right, next bit, we've got calculate the maximum vertical speed of the water surface. Well, we do this one a lot. So V max is A omega, which is A times 2 times pi times F. And we've got all of these, haven't we? Because we've worked out A and F. In this case, we're going to want to use the hertz one, really, because otherwise we get. You can stick with the per hour, I suppose. You'd have meters per hour, which is yeah. I mean, I suppose that would be fine, really. You don't have to keep going back to seconds, but I'm gonna stick with hertz, and we go with that. So we got 2.5 times 2, so 5 pi times F. So that's going to be 11 pi times 10 to the minus 5. So 1.1 pi times 10 to the minus 4. No, we're not really going to need this then. So we got 3.14 plus 314. So it's going to be 3454 with little bits. So 3.5 times 10 to the minus 4. And that's meters per second. So again, they've given us very nice numbers there, not needing a calculator. Write an expression for the depth D in meters of water in the harbour. Right, so this is just checking if you can understand transformation of graphs, really. So we know with our SHM, so remember that the harmonic part of SHM, that means we've got sinusoidal motion. So we've got this variation in a sine wave. And then we're doing transformations to a sine wave. And this could be sine or cosine. It doesn't matter which one we're doing, because of course they're the same shape. The only difference is a time shift. So it's deciding where our 0 time is, our t equals 0. So you can pick either of those on these, because they haven't said anything about what our 0 time is. So let's go with sine, but it really doesn't matter. So how can we change a sine function if we've got, I'll leave a bit of space there. So we've got some, we're looking at depth here. So if we were going to do D is some variation of a sine wave in time, Well, we can multiply it by some number all in all, so we can stretch it in the y direction. We can multiply the t by some number which is going to be stretching or compressing in the x direction, in the time direction. We could add on something to this this time here that is inside the bracket that we're taking the sign of, and then we could add some other value onto the end. Let's call that a d0. These are all of our shifts that we can do. We got stretches here and here in the y and the x direction. We got a shift in the x direction and a shift in the y direction. So they're all of our transformations that we can do. Okay, we haven't done a flip, but we can do a flip by, that would be included in this one and this one if we wanted to, you know, make things negative. So that's our general format, and then it's, well, what do all of these things mean? So let's start with this d0 at the end. That is our shift in the y direction. That's going to be our equilibrium point. You know, that is where we're starting, which is at 15.5. So we want to start off by saying, I'm going to move that to the front just to get it out of the way. So that's our 15.5, where we're varying from. So we can put that in initially. Then we can add our oscillation on top of that, which is all of this bit. So we need it to oscillate by an amount which is the amplitude, because our sine part of it is only going between 1 and -1. So this A is our amplitude. That's our 2.5 that we need to put on. Then we've got our sine. Now inside the bracket, this bit here, our phi that I've put on the end, I'm going to leave that out because that's just the phase shift in the x direction, as in we're moving the sine wave backwards and forwards in the time direction. And there's no point in doing that because that's just going to be deciding what our 0 point in time is, and I haven't said anything about that, so I'm just going to leave that out. We don't need to specify that at the moment, but we could put that in if we just want to line up our y-axis somewhere. You know, where were we at t equals 0? Are we starting here? Are we starting here? You know, what are we doing? So we've got some function of t inside the bracket, and that's going to be our angular frequency, because it's going to be to do with, well, how many oscillations are we fitting in inside a particular time period. So if we've got that as being our angular frequency, our 2 pi over t, or our 2 pi f, then in one oscillation, we're gonna, the t's will cancel. The t in here will cancel with a big T there, and we're just moving through 2 pi. So we're moving on to the next oscillation. So that's why this ends up being the angular frequency. Again, I've discussed all of this in the previous videos. We're explaining SHM. So we can put our angular frequency in there, which is our 2 pi f. Well, there's our f. So we just need to do 2 times pi times that. So yeah, so that is whatever it was, 11. Oh no, 2 times pi times this. I'm getting myself in a bit muddle now. 4.4 pi times 10 to the -5 in there. So that's our general format of SHM. Like I say, it doesn't matter which one you pick out of sine and cosine because that's just the phase shift away from each other. So you can take care of that in there, but we don't have to worry about that in this particular example. Yeah, so it's nice to get one of these tidal ones. They come up quite a lot because it's the one where they always do it for this description, it seems. This generalized description of SHM is very easy to visualize using these tidal patterns. Okay, I'm going to try and squeeze one more in, so hopefully this will be quite quick because I've already taken a while on this video. We've got a mass on a spring, we're back onto that. The mass is in equilibrium. By referring to the forces acting on the mass, explain what is meant by equilibrium. So there's two things we have to do. We have to say what equilibrium is. So equilibrium means we got no net force acting on the masses, So in this case, or just, was it mass or masses? What we've gone for? A mass, right, on mass. So in this case, it means that the weight is equal to the tension in the spring. So they specifically asked us to mention both things. So we've done that. Then we've got the masses pulled down 12 millimeters, then released, oscillates with SHM. Explain what is meant by simple harmonic motion. Okay, so we need that the acceleration is proportional to the displacement from the equilibrium position, and we need to say that the acceleration is directed towards the equilibrium position. So we got those two parts to it. Then we've got the displacement x in millimeters at time t. All right, so they've given us a format very similar to what we were looking at in the last question. We've got our amplitude there, and we've got our angular frequency there. Show that the frequency of oscillation is 1.25 hertz. All right, so we've got that omega is equal to 2 pi f, and we know that omega is 7.85. So we got that f is going to be 7.85 divided by 2 pi, which is 1.249. So 1.2 hertz to two significant figures. Oh, right, okay. Oh, no, they wanted 1.25. Well, it's close enough, yeah. I mean, it's pushing it to give it as 1.25, but I thought that was a show, that one. Calculate the maximum speed. So V max is equal to A omega, which is A times 2 pi f. So we want 2 pi. Oh no, they've given us, we've got omega, haven't we? Omega's 7.85. So we've got 12 times 7.85. And of course this is in millimeters, so we're going to have a multiplied by a 10 to the minus 3 in that. Yep, so 12 times 7.85 is that, and then the 94.2, 10 to the minus 3, so that will be 0.094 meters per second. Yeah, nearly went back and did the unnecessary of putting f in, when of course we've already got omega. Right, moving on to C. This bit down here, this blank graph, is for what we have to use in C. So this is giving us displacement against time, and they want us to draw velocity against time with a suitable scale on the velocity axis. Right, so we've got a phase shift going on here. We know what our V max is, this 0.094. So that's going to give us a sensible plus and minus on these. So let's go between 0.1 and minus 0.1 on those. We also know every time we've got a maximum or a minimum on here that we must be cutting the x-axis over here. So we've got that every 0.4. We'll be cutting the x-axis. Hard to see exactly where. Actually, it might be that line there instead. Hard to tell with these squares. So now we just have to decide. We know what our maximums are and minimums, but which way are we shifting this? Are we starting with a positive or a negative gradient on here? This is the key part of it. So if we're at a maximum displacement, so say we've measured down as positive, we've moved it down to maximum displacement, and then we let it go. Well, if that is positive downwards, our velocity is going to be negative because it's going in the other direction. So we're going to have to start with a negative gradient, then come down to here, up to here, and then back down to here. So we're going to have to do a sine wave that is looking that way round. Oh, bit wonky there. Hard with these pens. And it's meant to be hitting all of these points, cutting the x-axis, but it's a nightmare drawing them out on this screen. You should do a lot better on a piece of paper. But yeah, you need to make sure you're drawing it that way rather than starting off up here with a positive gradient and having, you know, the sort of inverse of this, because that just doesn't fit because of what we've said here. So yeah, that's covered that. That's given us our velocity against time. And we've put the scale on, because yeah, all of these are going to be, if we're drawing displacement time or velocity time or acceleration time, they're always sine waves. That's why we've got the H in SHM, you know, why it's all harmonic. We've just got different phase shifts going on, and we've got different multiplications. You know, we've got amplitude here, we've got a omega here, and then in an acceleration time graph, we've got a omega squared as being the maximum in the acceleration, so a maximum value on the y-axis. So we're just shifting these graphs around. It's just a straight transformation of graphs thing if you're looking at it from a pure maths perspective. Cool, right, that's wrapped up those three. So quite a long video, but they were 3 questions worth doing.